Hey guys, so welcome to today's video on Hess's Law. Hess's Law is, I think, just so much fun. It's like a puzzle. It's this really neat trick that we have to determine the value of an enthalpy of reaction or an enthalpy of solution if you're not able to do the calorimetry work. So the way this law works is if you can find some reactions whose equations can be added together to give you the reaction you wish you knew the delta H for, then adding up the enthalpy change values for each of those equations, adding them together gives you a sum, which will be the enthalpy change for your target equation. Okay, Lordy, that was like a whole bunch of what is she saying? So let's just jump in and do some examples. Before we do, however, I want to show you two really cool tricks that we'll be using. Okay, the first one says that if you reverse a reaction, the delta H is going to keep the same magnitude, but it will change sign. Here's what I mean by that. If you know that A plus B yields product AB, and you know the delta H for that reaction is negative 57, then if you reverse the reaction, products turns into reactants. So you take compound AB and decompose it to give you A and B. For that reverse process, the delta H is positive 57. Okay, that trick we're going to use a lot. Okay, and then here's a second trick. If you have an equation, you know it's delta H, and then you decide to change the equation by multiplying everybody through by some factor, then you're going to use that same factor and multiply the delta H. Here's what I mean. Let's suppose you have A plus 3B yields 2C. And in that equation, we have an enthalpy change of negative 100. All right, if I'm curious about then this reaction, half A plus 3/2 B equals C. Do you see how I simply multiplied each substance by 1/2? Well, the delta H for that new equation is going to be the original one multiplied by 1/2. Okay, so keep those two tricks in mind. And let's look at the first example. Now, for this lesson, I gave you 4 examples on a piece of paper. I suggest that you cut out each one and paste it at the top of its own paper because these sometimes take a lot of work. Treat them like a puzzle. This is fun. It's puzzle challenging fun. All right, so here we go. We have a reaction between methane and oxygen to yield methanol. And we wish we knew the enthalpy change for that reaction. We don't have it, and we can't do a calorimetry experiment with this reaction. But we do know that this reaction with methane, complete combustion of methane to yield carbon dioxide and water vapor, has an enthalpy value negative 802.4. And we also have, let's just say that we're getting these values from a reference book. We know that methanol plus 3/2 mole oxygen yields CO2 and water vapor. And that process has a negative 676 enthalpy change. All right, so we want to see if we can play with these two equations whose delta H values we know. Can we play with these two and come up with this guy? This is our target. So this is what we want to end up with. All right, so I am going to look at my target equation. I'm going to look at my first reactant, methane, and then I'm going to go down here to my two equations that I get to play with. And I see that this first one also has methane as a reactant. I want to end up with methane as a reactant. So I'm going to take this first one exactly as it is. I'm going to put it right here. And I know its value of delta H. It has an enthalpy change, negative 802.4. Okay. Now, my other reactant is oxygen. I only need half a mole of it. Okay, here I've got 2 moles of it. I'm going to skip over the oxygen right now. I'm going to look at the product. I want to end up with CH3OH. Well, neither of my of my play around equations has methanol as a product, and I need that. But I do see that my second equation has methanol as a reactant. So what I'm going to do is take this equation and I'm going to reverse it. I'm just going to flip it so that the methanol piece, along with the 3/2 O, is going to become a product, and the 2 products will be my new reactants. Now remember, we have this rule, this little trick that says if you reverse a reaction, delta H changes sign. And that's what I did here. I just took this original guy and I reversed it. Products became reactants, reactants became products. So my delta H for the new version is still 676, but now it's positive 676. All right, now I'm going to take these 2 and I'm going to add them together. So I'm kind of treating it like we do in math when you're adding a system of equations. Treat the yield signs like the equal sign. And let's put all of our reactants added together. So we're going to have CH4 plus 2O2 plus CO2 plus 2H2O. All of that on the reactant side. Okay, now my yield sign. When I do this work, guys, I try really hard to keep all of the yield signs stacked up vertically. Okay, so now on my product side, I'm just going to take all of these products and add them together. CO2 plus 2H2O plus CH3OH plus 3/2 O2. All right, now it's time to clean things up. I'm going to look for anything that is exactly the same on both sides of the arrow. For instance, do you see how I had 1 CO2 as a reactant and 1 CO2 as a product? So really, I'm just going to subtract that out from both sides of the equation. Likewise, I have 2 H2Os on the reactant side and 2 H2Os on the product side. So I'm taking them out. Lastly, I see that I have oxygen on the reactant side and on the product side, but not in the same amounts. Here I have 2 full moles of O2, and here I have 1.5 moles of O2. If I subtract 1.5 moles from both sides, do you see how these are gone? And I'm left over here with 1/2 mole of oxygen. And I'm also left with methane, CH4, plus 1/2 mole oxygen yields CH3OH. Okay, that is exactly my target equation. So what is the delta H? Hess's law tells me that if I can take equations and add them together to get my target, then the delta H of this target is just going to be the sum of these delta H's. I added the equations together. Now I'm going to add the delta H's together. And negative 802.4 plus positive 676 gives me negative 126.4 kilojoules per mole reaction. It's a puzzle. Okay, let's try another one. Let's try number 2 on your list. Looks like this. So this is our target. We would like to know the enthalpy change for this reaction. And we're not able to do this calorimetry experiment to find the delta H. But we do have information about this equation and its enthalpy change, and this one and its enthalpy change. All right, I focus on the target. Let's start by looking at reactants. I know I need P4 as a reactant, and I have P4 as a reactant right here. So I'm going to grab this guy, and I'm just going to write it again. So I did a little prep work here. I'm peeling pieces off, but you're just simply writing it again. And because we didn't change this in any way, I'm not going to change the delta H value in any way. Let's put it right there. Okay, I also need 6 chlorines on the reactant side, and I have 10. Okay, I am not going to worry about that right now, but I'm going to look next at my product needs to be 4 PCl3s. Neither of my equations gives me PCl3 as a product, but I do have PCl3 as a reactant over here. So I'm going to take this equation and reverse it. I'm going to make my reactants on the product side, and I'm going to put my product on the reactant side, which means my delta H has to change its sign whenever you reverse a reaction. Whenever you reverse a reaction, delta H changes sign. Okay, but now let's go back again. I really need to end up with 4 PCl3s, and I only have 1. So this is where I use cool trick number 2, which tells me, hey, if you multiply an equation through by some factor, just do the same thing to the delta H. I want to end up with 4 PCl3s, so I can't just change that one. I have to multiply everybody by 4, and then I have to take my delta H and multiply it by 4. And the value of that is going to be not 123.8, but it's going to be positive 495.2. Let me cross that out just so I don't mistakenly use it. Okay, so tricks. Line up your arrows. Look at what you want to have as reactants, what you want to have as products. If your pieces can add together to give you the target equation, then all you have to do is add those delta H pieces. So let's try adding the 2 equations together. P4 plus 10 Cl2s plus 4 PCl5s. Okay, that's everybody on the reactant side. Now my yield sign. And now everybody on the product side. 4 PCl5s plus 4 PCl3s plus 4 Cl2s. Okay, can we clean it up? Do you see that there's 4 PCl5s on both sides of the yield sign? So I'm subtracting them from both sides. And do you see that I have 10 Cl2s? And over here I have 4 Cl2s. So if I take away 4 from both sides of the equation, these go away. And on this side I'm left with 6. So I have P4 plus 6 Cl2s yields 4 PCl3s. And guys, that is exactly my target equation. So what is the delta H for the target equation? I added these two equations together. Now I'm going to add these two delta H's together. And negative 1774 plus positive 1495.2 is a net sum of negative 1278.8 kilojoules per mole reaction. All right, are you getting the hang of it? Let's do a third. So my third example, here's the target equation. I want to know its enthalpy change. And oh, this time I have 3 pieces to work with. Okay, so again, the strategy. Let's look at the first reactant. It's carbon. I need to end up with this equation that has carbon on the reactant side. And I see right here, my first equation gives me just that. So I'm going to put it right here. And because I didn't change anything about it, I'm going to take its delta H value. I'm not going to change anything about that. Okay, I also need 2 sulfurs on the reactant side. And let's see, I have second equation that has sulfur as a reactant. Notice that it only has 1. So I am going to keep that as a reactant, and I'm going to keep this as the product. But I am going to multiply everybody through by 2. Now, when I do that, the delta H for that original equation also has to be multiplied by 2. So my new delta H, let's see if I can find my work here. I am multiplying this by 2, so that's going to be negative 592.2 kilojoules per mole reaction. I'm going to take this guy away so that I don't inadvertently use it again. Okay. Looking back at the target, I know I need to end up with carbon disulfide on the product side, and the only place I see carbon disulfide is over here, and it's on the reactant side. So I'm going to take this equation and flip it around. Make reactants become products, and the products become reactants. And when I flip an equation around like that, I take the delta H value and change its sign. That's kind of sloppy. Okay, now let's see what happens when we add these 3 equations together. So I have carbon, I have oxygen, I have 2 sulfur, I have 2 oxygen, I have CO2, and I have 2 sulfur dioxide. Okay, that's all my reactants. And on the product side, I have CO2, and I have 2 SO2, and I have carbon disulfide, and I have 3 oxygens. Okay, that's a hot mess. Let's clean it up. Do you see anything that's exactly the same on both sides? And I see 2 SO2s and 2 SO2s. If I subtract that from both sides of the equation, I'm good. How about the oxygens? Here's 1 plus 2 more, that's 3. And on the product side, I have 3. So I'm subtracting 3 O2s from both sides of the equation. And let's see, 1 more. I see CO2 on the reactant side, and I see CO2 on the product side. Subtract that from both sides. And that leaves me with carbon, sorry, excuse me, plus 2 sulfurs yields carbon disulfide. And that is my target equation. So how do I find the delta H for my target? Since I got the target by adding these 3 equations together, I'm simply going to add these 3 delta H's together, and I get delta H is equal to positive 86.3 kilojoules per mole reaction. Alrighty, let's do 1 more, and then I'll let you try some on your own. Here's number 4, target equation, 3 equations to work with. Okay, if you're feeling brave, you could pause, try it yourself, and then come back and listen to me walk through the answer. That's a good idea. Why don't you pause it? Okay, now we're back. So let's see. I need to have 1/2 mole of N2 as a reactant. And the only place I see N2 is right here. So I'm going to use this equation. And it's going to go here. Remember this tape. And here's product. Come here, little guy. Okay, so I'm keeping this in the same order, but I don't want 1 full mole of nitrogen, I want 1/2. So I'm going to multiply everybody by a factor of 1/2. And that'll be 3/2, and this will be 2/2, which is simply 1. And since I multiplied everybody through by 1/2, I have to do the same thing to the delta H. And 1/2 of this is negative 45.9 kilojoules per mole reaction. Okay, let's see. We need some oxygen. I look down here, I see oxygen in a couple places. So I think I'm going to pass over that for right now. Focus my energy on the product NO. And the only place I see NO is in this middle equation. It is on the product side, so that's good. So let's just take it and put it right here. The problem, though, is that I only want to end up with 1 NO, and I have 4 NOs. So let's divide everybody through, or actually, better way to say it, let's multiply through by a factor of 1/4. So 1/4 of 4 is 1. 1/4 of 5 would be 5/4. 1/4 of 4 is 1. And 1/4 of 6 is 6/4. And then 1/4 of negative 906.2 is negative 226.55 kilojoules per mole reaction. Alrighty, so I have NO on the product side. I have 1/2 N2 on the reactant side. Let's see. I need to get rid of NH3. Oh, that's going to happen here. Let's see what else needs to happen. I need to get rid of hydrogens. I don't want hydrogens on the reactant side. Here's an equation that has hydrogen on the reactant side. If I want to get rid of it, I want it to end up over here on the product side. So I'm flipping this equation. Are you still staying in the, this is just a puzzle frame of mind? Some of them are hard. Okay. So I flipped this equation. I know delta H is going to change sign. But you know what? I also need to, what do I need to do here? I need to multiply everybody through by 3/2 because I have 3/2 hydrogen and I want that to cancel out with 3/2 hydrogen. So let's multiply through by 3/2, 3/2, 3/2, and 3/2 times 1/2 is 3/4. Sorry guys, this one's kind of ugly. Okay, I multiplied everybody here by 3/2, so I have to multiply by delta H by 3/2, and that would be a positive 362.7 kilojoules per mole reaction. All right, now let's add up all the ugliness here. Okay, I'm going to write down all of my reactants. I have 1/2 nitrogen. I have 3/2 hydrogen. I have, oops, I'm almost off the page. I have an NH3. I have 5/4 oxygen, and I have 3/2 water. Okay, those are all the reactants that I've added together. And on the product side, I have an NH3, I have an NO, I have 6/4 water, I have 3/2 hydrogen, and I have 3/4 oxygen. Oh, Lordy, I hope we can do some cleanup. Okay. 3/2 hydrogen on both sides of the equation, subtracted out. NH3 on both sides of the equation, subtracted out. 3/2 water and 6/4 water. 6/4 is the same as 3/2. Get rid of those guys. Okay, lastly, I have 5/4 oxygen and I have 3/4 oxygen. If I subtract 3/4 oxygen from both sides, it's gone here, and 5/4 minus 3/4 equals 2/4, which is also equal to 1/2. So I have 1/2 oxygen, I have 1/2 nitrogen. That's all that's left on the reactant side. And on the product side, I have NO, and that's it. And this is my target equation. So what's the delta H for the target equation? Well, since I got the target equation by adding these three pieces together, I'm going to add this delta H, this delta H, and this delta H together. And the sum is positive 90.25 kilojoules per mole reaction. If you tried that one on your own and you got the right answer, then congratulations. Okay, keep in the puzzle spirit of things, and we'll do some more practice on these till you get really comfortable with them. Okay, guys, I hope that was helpful.